Okay, please.
So in this talk, we will tell you about some results of us connected to the reduction of dynamical systems over monoids with concrete applications. Okay, so not pure theory, but with, as written in an email, with concrete application. So the talk is structured in this way, a bit of history. In fact, Max and I, we are working on model reduction since many, many years, actually. We are getting old. It was probably 2014, Max, when we started. But Max started earlier, but together we started in 2013. So a bit of history, then some preliminaries on discrete time systems and specifically Boolean networks, which are models used in biology, the state space and the dynamics of this model, attractors, state and issues connected to analyzing these models. Then we will present a reduction technique we proposed, and we conclude with some results on experiments we performed on online repositories. So a bit of history. Max and I started working together on these reductions in end of 2013. Max started actually earlier, also already during his PhD. And in 2017, we got this paper of which we are very proud, very happy. It was more or less in the time in which we separated. I went to Denmark, to Copenhagen, and Max went to Aalborg. So it was a nice way to conclude that part of our story. We together with Mirko Tribastone, who was the senior guy at the time, we were postdocs with him, and we had the luck of collaborating with Luca Cardelli. So in this paper, we propose two reduction techniques for ordinary differential equations, and in particular, polynomial differential equations. So systems like this, with this number of variables, if you analyze, if you set some initial values for the 6 variables in this model, you get only 3 traces. Why? Because these variables to which we gave same color, pairwise represent the same dynamics if initialized equally. This is the notion of and we are able to discover this property, and this is what we call backward reduction. So we make a simpler model with fewer variables, only 3, preserving all dynamics in the model, okay? The second reduction, family of reductions, which is connected to what we're going to tell you today, is the so-called forward reduction. We also call it coarse graining. It is becoming a hot topic nowadays in network theory. So the idea is that in this model, we have 4 variables, but only 3 traces. Why? Because let's say we are not interested in studying red, blue, and blue, red, which are 2 different variables. We are interested only in their sum. So even if we have 4 variables, we plot this green trace. This green line is the sum of the 2. We can get a simpler representation of a model with 4 variables into 3, where the green variable represents the sum of the 2 original variables. So the model is simpler to analyze, and we preserve not all the dynamics, but all the dynamics of interest in this case. The modeler tells, I want to preserve blue, I want to preserve red, I don't care about the other 2, so they get lumped, aggregated in the same variable. In this paper, we did an application to a discrete time model defined over the Booleans. These are Boolean networks. In particular, there is a technique named odification, which allows you to transform Boolean networks, this Boolean model I will tell you more about later, into ODEs. So in an indirect way, we can reduce Boolean networks. And one of the reasons why we got this PNAS paper is that we had Boolean networks applications. The reviewers liked them. Why? Because these are models used in biology to talk about important things like the immune reaction to HIV and other diseases. This is a model widely studied. So after that paper, we decided to develop from scratch reduction techniques for Boolean networks because the codification encoding was difficult, was not giving, was taking a lot of time to be done, was not scalable. And if you work on Boolean networks, you want to stay in the realm of Boolean networks. You don't want to get reduced ODs. So after this paper, in 2023, we get a leaks paper presenting essentially a generalization of this forward notion directly for Boolean networks, but actually for difference equations and also for nonlinear ODEs. And we get a nonlinear reduction, what we call monoids, reduction over monoids. We don't just sum variables, we can also multiply variables and more. We also got a bioinformatics paper.
Excuse me, Andrea.
Yes.
Here you use nonlinear in a more general sense than polynomial. You speak about polynomial and data
No,
more general.
In this case, it's still polynomial, but we have also reduction techniques for ODEs, which are with greater nonlinearities. We cover the entire decidable fragment of reals of Tarski. So everything but trigonometrics and exponential, right, Max? Or yes, okay. And we do that using, yeah, we're not going to talk about that. But no, in this case, nonlinear means polynomial. But also in that case, we use SMT tools. But okay, today we know. What we do really important nonlinear is that we don't sum variables. We can multiply variables. We can apply other operations. We also re-implemented the backward reduction directly for Boolean networks. In this case, we got this domain-specific journal. We have shown in all our papers, we were lucky in finding many real models where we could apply our techniques. So that's it for the history. So Boolean networks. Before getting to Boolean networks, I need to tell you about influence networks, which are also known as signed graphs, signed direct graphs. Here I have three variables, and let's say biologists don't know specifically how these three variables evolve, how these three species evolve. They only know that when X3 is present a lot, it will tend to turn off X1. So X3 is an inhibitor of X1. It has this negative effect. Instead, X1 has a positive effect on X2. And you can also have self-effects. So often biologists try to get this information. You can get it from in vitro experiments. You can get them automatically from time series of some measurements. Once you have this, you can synthesize a model that you can animate, that you can execute, an operational model, which is a discrete time system defined over the Booleans. This is a Boolean network, okay? This is an intermediate representation. If you execute this model, you get the state transition graph. Each state is a vector of active, not active status for each variable, okay? And what you are interested in is studying attractors, single steady state attractors or cyclic attractors. Biologists believe that attractors represent different functions, different statuses of the system you're studying, like tumor, not tumor. Active, I noticed an infection, I didn't notice it. These are important, and there are many techniques to control Boolean networks, to move the state from one attractor to another. We don't work on control, we work just on analysis of Boolean networks. The problem is, as usual, state space explosion. If you have n variables, the state transition graph, the state space will have 2 to the n states. So we propose a reduction technique that gives you smaller STG, but often too big to be analyzed anyway. Faster computation of attractors. Attractors are computed without fully enumerating the STG, the state space, so you can analyze more. And also it facilitates control techniques applied to Boolean networks because you have simpler Boolean networks. This is just one of the many models that can be found available online. This is a model of a cell in our blood which detects infections. It is on purpose in 2 slides to stress that it is very big. It contains 128 variables. So if you start building the analyzing attractors with state-of-the-art tools, you cannot do it. Our reduction techniques allows you some fine-tuning. You can stress what you want to preserve. So we can see that original model cannot be analyzed. A model reduced just a little bit cannot be analyzed. Model reduced a little bit more can be analyzed, and you get 8 attractors. If you reduce more, you get less attractors. We don't lose attractors. We collapse them, okay? So in some sense, we lose information because we don't know how many attractors there are in this model. The largest numbers of attractors we could compute is 8. If we reduce more, these 8 attractors get aggregated into 2, but at least it could be done. Before, it could not be done. This is another even larger model. I forgot to tell you that in these Boolean networks, some variables are known as inputs. Typically, they don't have dynamics. The modeler sets 0 or 1 and checks what happens, like a pachinko game, if you know this Japanese game where you put a coin and things go down. They set 0, 0, 1, some other values, and they check what happens. These are inputs. Instead, outputs are variables at the bottom. Sometimes you don't care about what happens inside. You only look at the system, looking at the values of these output variables. So what we do, since we aggregate variables, we can say reduce, but try to keep all output variables into one block. No, put each variable into a separate block, which means preserve all single outputs, which from an external point of view means you don't lose any information on the outputs of the model. Or which is this one, maximal. Or we try to preserve only some of these outputs and we get larger reductions. So in this case, original model could not be analyzed. This model, sorry, this reduction is the one where we try to preserve all outputs. It could not be analyzed. O1, O2 is a setting where we preserve some of the outputs of the model. Again, we can analyze the model very quickly before it could not be analyzed. Okay. These are some other experiments regarding the generation of the transition, the state space. If you go, at least at the time we did these experiments, it was not possible to generate the state space for more than 20 something variables. So it was important to be able to go down. So 24 was the largest number of variables for which you can generate the state transition graph. Instead, for attractor computation, you can go higher. And 170 is a good number for Boolean networks. This Boolean network has 300 variables, but these are very seldom. Typically, you have less than 100. So we can really make a difference. This is an example where we have a system with 3 variables. These are the update functions. We aggregate x1 with x2. So we get one derived variable, x12, which corresponds to the OR of the first 2. So if you build the state transition graph, you get a simpler one which is interpretable in some sense. 0 means that both x1 and x0 were false. 1 means either one of the two was true. You lose some information, but you preserve this aggregate information, okay? So we went beyond plus by supporting OR, AND, XOR, and more. Is it everything clear so far? Do you have any question, any clarification question? Should we go on? So we find variables that can be put together. We rewrite the system algebraically, obtaining a variable, a derived variable which represents the OR of two or more variables. And this model is a Boolean network, can be analyzed with any technique for analyzing Boolean networks. And the modeler knows that 1 means that either x1 or x2 were true, the OR.
So,
I have a question. Can I ask you a question? So like, are you choosing yourself as an input that I want to aggregate x1 and x2, or
No,
you have a
no,
system where you're finding all of the ones that are like
no.
easy to aggregate?
We have a partition refinement algorithm, which means the maximal reduction is, these are my variables, try to aggregate all of them. Or you can say, I want to preserve this variable, I want to preserve these. So I put them aside and I put all of the others in one set of variables to be aggregated, and I only aggregate them automatically. And our algorithm gives you the maximal reduction, the best reduction, the one with least number of variables. Okay? So partition refinement means in general, it tries to give you the least number of variables possible, but you can also impose some constraints. Try to preserve each single output because they are interesting. I don't care about all the rest in the middle, because what I do, I put values in the input and I check what happens in the output. Try please to collapse everything in all internal nodes. Okay, so we have a partition refinement algorithm. Max will tell you more later about it.
Excuse me, go back, please. Go back one slide. Yes. To provide this reduction, you should be very lucky, because here you can use x1 and x2, but the reason that you can use this as a new variable is that you have a system of very special structure. How do you know this? You can say that I am interested only in x1 and x2, but if you have a system of equations of different form, then you cannot do this.
So Boolean networks are Boolean expressions. So we have not and or. Is this what you mean, or
once again, please?
Can you repeat what you said about specific
my
structure?
problem is that here in this very simple example, you have a look at the system of equations and you realize that x1 and x2 can be lumped together. But if you have a very large system, you may be not as lucky as here. But
we don't do it by eyes. We have a technique, a fully automatic technique.
Yes.
Given a Boolean network,
yes,
gives you the smallest reduced model obtained by collapsing variables.
Okay,
so
we do this automatically. Okay,
we start from one large set of variables, and we split this set into smaller sets. At a certain point, we stop, and when we stop, each set becomes one variable. And we characterize this property, being able to express variables as the OR of these blocks. We have characterized this property. Maybe later it will be clearer with definitions. So
yes,
I start telling you about two variables, but in reality, we work on partitions of variables. So a Boolean network is made of a set of variables and a set of update functions, like this. We guess, but it's not true that we guess. I'm just showing you what happens. we guess that x1 and x2 can be lumped together, can be aggregated. So we take the update function of, so we aggregate the update function. We do the OR of the update function of x1 with the update function of x2. You see, x2 or x3 is this one. x1 or x3 is this part here, and we put them into OR. And since we are lucky, as Janos said, we find that we get an expression given in terms of the OR of the two variables that we want to aggregate. In all update functions. This must happen in all update functions. So we can rewrite this system like this. We already have a reduced model, just done by algebraical steps. In reality, what we do, we ask Z3, we ask an SMT solver, a SAT solver, for the validity of a given formula. We check whether this formula holds. So we take the OR of the two variables is equal if you put to 0 x1 and you replace the other guy x2 with the OR of x1, x2. In some sense, I'm saying I can move mass around. I can cancel x1 from the model, replace it with false, with 0, and I replace x2 with the OR of the two variables that I want to reduce. And this property must hold in all update functions. I repeat, we create a SAT formula where we ask, you want to reduce x1 and x2 together? Okay, then this formula must hold. Please take the update function of the two variables, so x2 or x3, x1 or x3, do the OR of them, and this OR must be equal to the OR where you set to false x1 and you set to x1 or x2 the other variable. Anyway, we build automatically a SAT formula. If it is valid, actually, this formula is valid if and only if the system can be rewritten as the OR of the two original variables, aggregating the two original variables. We have a theorem for this. In reality, we work at the level of partition. Partition means we have sets of variables. P1 contains some variables, P2 contains some other variables. If we build another SAT formula for this partition, if it is valid, then we can reduce the original system with one variable for the first set of variables, for the first block, one variable for the second, one variable for the third, and so on. So the reduction that I was trying before is done in this way. We have a partition where we say x1 and x2 are lumped together, x3 stays on its own. We preserve x3. So we build trust me, we build a SAT formula for this, where we compare the OR of the variable in each block. We compare it with the same, the combination of the two functions, replacing variables with 0 and doing the OR. So we do this for every block. So given a partition, we build a SAT formula. And we don't write the partition ourselves. This partition is obtained, as Max will tell you, automatically. And we have formal guarantees that we give you the best possible partition, the partition that gives you smallest model.
I think now the number of possible partitions is again very large. No?
Yeah. Instead, we do if you ignore the complexity for the SAT, that's if you consider that as constant, the rest of the algorithm takes polynomial number of steps because you refine. And in fact, the PNAS paper on ODEs, we have polynomial complexity, polynomial time and polynomial space complexity. Here we don't have polynomial complexity because we have a SAT solver in the middle as a basic step. But if you think of the SAT solver as something constant, if you ignore it, Then we do polynomial number of steps. The idea is that you start from a partition. You can only refine it by splitting its blocks. So there are not combinatorially many splits you can do. Max, do you want to share?
Yes, thanks, Andrea. I will try to share. Let's see whether it works. Okay. Okay, do you see nice slide? Please let me know.
I can see the slides.
Okay, thanks. Okay, good. So yes, thanks for the first part, Andrea, and also thanks, Janusz, for the kind invitation to the seminar. So as anticipated by Andrea, now I will try to give first the idea how we can generalize the whole thing, because so far we spoke about Boolean networks, but now we are going to do monoids, and then later I will speak about the actual computational algorithm. Okay, so this formula you have seen on the last slide. And the idea was essentially that in the case of Boolean networks where we make reductions up to the OR, we were taking the neutral element, and then we were replacing essentially it using this kind of schema here, or scheme. So now if you want to go for the general case, the monoid case, what we do is essentially, and here we annotated essentially by the color, we replace the OR by a general monoid operation, and then we replace the neutral element with respect to the neutral element of the monoid in question. But the whole structure in the end of the day remains the same, and that's pretty much it. And with this, we can give then at last the definition of what. Okay, first we fix. Now we want to give the main statement. So first we define which kind of dynamical system we are actually looking at. The idea is that we want to see, just a second, yes. So we want to see, we have I don't know whether you see my cursor, but essentially we pick a dynamical system that takes n elements over the monoid M and maps then it to the new value in the monoid M. And this is the type set of families of dynamical systems over monoids. And now we call a partition P of the variables of this monoid forward by simulation if it satisfies this condition here, which is essentially what we have seen before. And that was pretty much it. Before giving you the actual algorithm, I think I want to give you a kind of high-level idea what we can actually do with this stuff. So concretely, examples of monoids. And so here in the top, you see the monoid where we have the real numbers and the plus. And this corresponds essentially to the classic theory of lumping you may know, where you essentially have a projection, orthogonal projection, or any projection if you like, to a smaller dimensional space. And the linear mapping is essentially given by weighted sums, which are, in the end of the day, pluses, right? So now if we would consider the monoid instead, where the operation is times instead of plus, we could cover not just sums of variables, but products of variables. And to give you an idea, next slide.
Some animation got slower, Max. You have to click a few more times.
I see. So let me go back. Sorry for that. From the current slide. Good. Okay. Okay, so let's consider this as a toy example, really. Now, the Lotka-Volterra model, where you have intuitively, well, what do we have? We have one prey that is being preyed upon by two predators. The predators are X2 and X3. And you can see essentially that you go down with the speed of the product of those two guys. Now, since our framework here is actually discrete time and not continuous time, if you want to consider this continuous system, we need to discretize it. And we can do it, for instance, using the Euler method, which is the easiest discretization scheme, numerical scheme for the numerical solution of differential equations. And you would get this discrete time system. In principle, you could also use more complicated things.
Excuse me, Mars, just a
Yes,
not
please.
relevant remark that usually Lotka-Volterra models have a linear second factor. You have a nonlinear second factor in the first equation. So usually it is understood that the second factor is linear, right?
Okay, so to
This is
which
what is
ODE
usually
are you referring now?
You
Janos?
may say that it is a generalization of something, but is different from Lotka-Volterra, but how usually use this term. Okay, not relevant. I just remark this.
No, but out of curiosity, I would like to understand what was the remark.
The first equation,
In the
like
first
partial.
you have a nonlinear.
This one, yes, this is not the usual Lotka-Volterra because here you have 3 species. Indeed, you don't have 2 species. You have one parameter.
Yes, but it is not about the number of species. It is about the right-hand side of the first equation. The right-hand side of the first equation is a product, and the second term is not linear. This is usually not called Lotka-Volterra. You may call it Lotka-Volterra, but you should mention that this is something different what people usually call Lotka-Volterra. And not because of the number of variables.
I can send you a paper.
Not important.
This is called generalized Lotka-Volterra model.
Yeah, you can say something like this, yes. It is a Kolmogorov-style equation if you like. But never mind.
Okay, so this generalized Lotka-Volterra model, which uses essentially now 3 species here instead of 2. If you want to analyze it or if you want to aggregate it, we need to go to discrete time. So we do this by applying discretization. And once we got this discretization out, we can actually now apply our machinery. And what we discover is that the partition that can be aggregated here is singleton variable x1 and then a block that contains x2 and x3. So this is essentially what we get, and which is essentially a nonlinear now reduction in the sense that the mapping that is being induced by this partition is nonlinear because it involves a product rather than a sum. Now, in case of Boolean networks, or in actually multivariate networks, we can use essentially finite fields if you like. And then we can encode min or max using essentially, well, convincing ourselves that over those structures, it's min and max defines a monoid. And with this, we can reduce discrete time dynamical systems over these domains, which are given on the right-hand side. Also, I think examples from those models we came across, which are in some sense given in this kind of case definition style. Okay, so now at last we come back at the anticipated reduction algorithm. So the rough idea, I mean, okay, there are many symbols here, but the rough idea that we would like you to understand here is that we start with some partition, which is, well, actually we start with an initial, yes, XR here, and we are given a dynamical system. X is are the variables, F is the update function. Now we have here this while loop, which is essentially taking the partition that we store in H, and then it does something and it refines it in the end of the day in this for loop to H prime. and I will tell in a second how we refine it. But the point is, once we identify that the new refinement is equal to the old partition, we know that we cannot refine any further and we stop. Now, the refinement itself happens here. And in the end of the day, what we kind of define as an equivalence relation that is given by this function here, which tells you, I mean, this formula is true when we consider x1 and xi and xj to be equivalent to each other. And if they are equivalent to each other, they go into the same block. If they are not equivalent, then we split. And please pay attention. This formula depends on xr, which is the current partition we use. So here it is, I mean, h. So the current block, the current partition we have is used to define the splitting criterion. And then once we have computed all the splits, we update, we get the new partition. And as Andrea said, the key, if you want to identify that this or that is being split or not, this you pick or can regulate by picking xr at the beginning. So if you want certain things not to be split or to be available, you put them into singleton blocks, and everyone else that you don't care about, but you want to get the best possible reduction, you put in one big block. And then you run the algorithm and you will get the largest possible partition with respect to the initial partition you got. Okay, good, enough algorithm. Here are now some here are now actually the applications. So what did we do? We considered 2 repositories. Well, actually 3, but at this point 2, where we took 29 Boolean networks out of the GenSim and biomodels repository. And here on the right, you see the reduction ratios for the operations and OR over those Boolean networks. Here you have the numbers, which are essentially the labels of the models. I mean, those models have specific names from these databases, but we just enumerate them. And then we sort with respect to the reduction ratio. Reduction ratio of 0,1 means that we reduced from 100% the original size to 10%. So the smaller, the closer to 0 we are, the more aggressive we are in the reducing. And we can see that for some models we get very aggressive reductions, and then, okay, since we are sorting with respect to the reduction ratios, the more to the right we go, the closer we get to 1, which is essentially no reduction at all. Nevertheless, we can see that we get decent reductions on a number of models. And we want also to say that those reductions are useful because we were essentially able to consider then the respective runtime ratios where we were computing, doing the attractor analysis. And we were faster in with respect to the original models. Yes, do I want to say here more on this? Maybe I go on the nonlinear reductions. So for the nonlinear reductions, this was another repository, the third one, which was NetSchleuder, I think. And yes, we considered 72 weighted networks with up to 200 nodes. So there are more networks, but we limited ourselves to those with 200 nodes. And we considered now, so given this graph, a weighted graph, we associated to this weighted graph or adjacency matrix dynamical system. And in this case, in the case where we considered the discrete time, we did essentially this, which is commonly done in many disciplines if one wants to associate a dynamical system to a graph. And we considered also the continuous case, where what I want to say here, or we want to say here, is that the continuous thing here is actually the Euler discretization of the system. And to the right, you see the reduction ratios, which and again sorted with respect to the models. And you can see that we get, we can obtain also quite, in some cases at least, very good reductions. Both models, the discrete and the continuous, behave similarly, but I mean, they are not exactly the same, and therefore this is also why the two graphs are not exactly matching. What I want to say here is that this is probably the most important one, which I should have stressed more. This reduction that we considered here was up to the monoid, the product monoid. So as written here. So if we were putting variables together in a block, it means that we were obtaining as the reduced variable, the product of the variables in the block. So while we start with a linear dynamical system, we obtain a nonlinear, well, the mapping is nonlinear. Okay.
I have a question.
Yes.
Sorry. So you are using monoids, and like you're saying, for example, reduction with and reduction with or here with reduction with respect to the product. Can you do both? Can you? I know it's not monoid, but like, can you do one reduction, another reduction? Does that help? If you do like reduction
Yes.
with
I mean, in principle, you can combine reductions after the other, and hope to, and you will get a reduced system. You have just to be careful if you do the sequence to have a logical relation to the original model, because if you do one reduction, you are guaranteed to have a logical connection to the original model. But say now you do first min, and then you do max on the reduced. Then what then? Then you have essentially the first connection to the, what you would essentially have is as a kind of min-max variable, right? Because if the first step is doing kind of the minimum across the original variables, then the second will do a maximum across the minimum. So you have a max min in this case. Does this?
Okay, it makes sense. So you're losing a little bit of the interpretability.
Yes, you have to be careful that things kind of that the information you get is useful to you. It may be useful, but you need to be careful what you're doing. I mean, it's a kind of general remark, really, because you can often combine reduction techniques with each other. Like you do, for instance, a fast-slow decomposition, and then you do orthogonal projection or whatever. Here you can also do this kind of playing with different monoids, yes. Okay, now if we compute those things, then we need to check to evaluate maybe, well, okay. You remember this in the partition refinement algorithm, we had this formula psi, and in order to evaluate this formula psi, if it starts to have, well, if you need to check equivalences between polynomials, well, you may have a hard time because you need to check the polynomial identity test. But if you say that you're happy of working with randomized algorithms, then you can use essentially the Schwarz-Zippel lemma to do a very efficient randomized algorithm around it. And this is actually what we did here in those experiments, because the direct calculation with Z3 was, as expected, scaling not that far. Yes. Okay, future work. There are several ways to go about this. We could think of on-the-fly computation of GFB, which is a kind of on-the-fly, is a term from maybe computer science. The idea is essentially to say that you evaluate only partial checks, so psi formulas, and then you kind of get maybe not the most aggressive reductions, that is not the smallest possible model, or not the smallest possible reduction, but you can identify whether two variables can be aggregated or are not aggregated. for instance. Then extension of hybrid dynamical systems, where, I mean, this framework is now fairly general because you can essentially put, as long as you have a monoid and discrete time, you are happy. Actually, also continuous time, we have in the paper, we did not show the theorems here, but in the paper, we have connections that formally connect continuous time to discrete time. So I forgot to say this. And reduction of dynamical systems over arbitrary functions, which is kind of relating to the question of Janos from before, where we could try to incorporate into the framework, for instance, rational functions, which would fit nicely in, because, for instance, Schwarz-Zippel lemma is also applying there, or more complicated functions, like, I don't know, root and so on. But of course, we would have limitations here because at some point, as Andrea was saying, we would hit the decidability business, because if we start doing sine and cosine, then things become tricky. Okay, I think that's it. Thank you very much for the invitation and for your interest.
Thank you, Max, and thank you for Andrea.